Welcome everybody to today's dissertation defense of Nick Saunders. I want to say a special warm welcome and aloha to Nick's family, who's with us here today. His parents, Sister Mary, Anne and Steve, his parents, and Sister Mary. We're making a long way to come here. And other family members we haven't met yet.
Molly.
And Molly, welcome. And Brittany, of course, who had a much shorter commute at first. So for those of you who don't know how these things work, so I'll just recap. The procedures here will be that Nick will give a talk about his dissertation, which will take about 30 to 40 minutes. We'll then have about 10 minutes for questions from the audience. After that, I'll ask everybody but the committee members to leave. We'll have a closed examination session, and if all goes well, if Nick passes, we'll have a little celebration down in the courtyard. But before we do all this, I'll continue the tradition of giving you a little bit of an introduction as to how Nick made it here today, defending his PhD in astronomy. And as usual, at this point, the students probably think, how far back in their lives did we manage to dig up pictures? And I'm very happy to say that once again, I had very good support, which shall remain anonymous, although you can probably guess it, to provide us with lots of pictures of Nick. Here you go. I'm going to make sure you see this too. So here's Nick. Very young, very excited. So Nick grew up in northern Washington State, in a town called Winthrop, in the Cascade Mountains. And was, of course, growing up in the mountains into winter sports. So you can see him skiing here. One of the stories that was relayed to me is that Nick was so much into tricks while skiing with his friends that he actually got kicked out of the skiing team. So he was very adventurous and into a lot of doing spectacular tricks, hanging out with his friends. So here's some his childhood memories with friends. And of course, his sister, Mary, who was here, is 5 years older, and as I've heard, actually shares the same birthday, which I'm sure made for some interesting birthday parties throughout the years. Of course, Nick developed as a fascination for science. The evidence is here in these pictures, which just randomly put together, but you can see rockets, microscopes, being very good at math early on, chemistry experiments that I don't really know much about. But one anecdote that was relayed to me, which I actually relate to a lot, was that it was a very influential teacher for Nick in preschool, Little Star School in Washington, that sort of fueled his passion for science. I think he wanted to do a chemistry experiment, and the ingredients for the chemistry experiments were gathered by the teacher. Unfortunately, she couldn't get all the ingredients because some of them were actually explosive. So couldn't go through with that chemistry experiment. But the teacher was very influential in Nick's path to become a scientist. So as he went on, of course, he went to university. That was at the University of Washington. Many of you might not know that Nick has a second passion apart from physics and astronomy, and that is film studies. So he actually did a degree in film studies. I hear from sources that there are two reasons for it. One of them was, of course, that Nick likes movies. There's some evidence for this even in his dissertation, including this quote, which I know nothing about, so you'll have to explain to me at some point. I've not watched the movie, so. And Nick is a big fan of, apparently, of Nick Cage movies, which I know really well, actually. I grew up with it. Apparently, Nick even invented a drinking game that goes along with Con Air. So once you get a PhD, you'll have to tell me more about that. As part of this, of course, was also meeting his partner of 10 years now, Brittany, at the University of Washington, who also at that point actually did film studies. And I think part of the motivation perhaps of Nick continuing in that vein was that he could spend more time with Brittany. Eventually, Nick moved on in between undergrad and graduate school. He spent some time at NASA Ames. This is actually quite near and dear to my heart because I actually did my first postdoctoral fellowship at NASA Ames. In fact, my office was exactly in that same building that Nick is standing in front here, N244 at Moffett Field, where the Kepler team is working. So I did my postdoc there a few years before Nick joined the Kepler team. Obviously, Nick fell in love with Kepler. He fell in love with exoplanets, and that continued to this day and followed him throughout his PhD. Of course, he got into lots of adventures, as most of our graduate students do here. Once he moved to Hawaii. So here's some pictures of the beach, birthday parties in the bowling alley, I think, with fellow graduate students. This picture here is from a recent, last year at a conference in New Zealand, Extreme Solar Systems and a camping trip. One other thing that Nick apparently likes to do, and I really like this quote from someone who also shall remain anonymous, he likes to cook for his friends. So the quote is, a lot of my best memories with Nick are him cooking dinner for his friends and watching something dumb. This really relates to movies. Okay, Nick, of course, went through the usual trajectory as a graduate student here. Here's Nick on the summit of Mauna Kea with his graduate student, fellow graduate students, and in front of the Keck telescopes, which Nick used extensively during his PhD. He spent a lot of nights observing. I don't actually know how many, you probably know, but I'm sure it was several dozen of observing nights using Keck. A lot of the observing, of course, nowadays being done remotely, as seen on the picture here on the right. So one of the things I do want to sort of, as we wind down this introduction, is how did Nick actually get to work with us? So I like to dig out these emails, which is the very first email that I got from Nick from his NASA email account, saying, hello, Dr. Huber, I recently applied to Hawaii PhD. The work you do is very interesting to me. Here, of course, and I'm contacting you to let you know I'd love to work with you on multiple areas listed on your website. Of course, at that point, the standard faculty reply is, that sounds great. I'd be happy to work with you if you get it admitted into our graduate program, which of course we often don't have a lot of say over. But luckily, Nick actually got admitted, of course, to UH and ended up here, and we ended up working together. And Nick's academic path was highly successful. Here are the titles of the 4 first author peer-reviewed research papers that Nick led, which he will tell us about a lot more. I want to emphasize here that there, in addition to this, there are about probably, I think, about a dozen or so papers where he made very substantial, i.e. second or third author contributions to. The other thing I want to point out that there's as many times here, as is the case with many dissertations, this is a team effort. I'm standing up here cracking the jokes, but really, Jen was very instrumental with this first paper here as a lead advisor and also as the co-chair of Nick's dissertation committee. And in particular, also Sam. So you can see here that I'm actually not second author to any of those papers. So I didn't actually do much at all in Nick's PhD path. But it was Sam. Sam is second author on all the 3 main papers that relate to tests. And many of you will know that Sam actually did his PhD here many years ago. He's now faculty at the University of Alabama. And so I'm going to hand over to Sam to wrap up the introduction, given that he's actually done most of the work.
Well, thanks, Dan, for giving me too much credit, because I didn't actually do most of the work. Nick did most of the work, and that's why he's the first author on all of these papers. But yes, so as soon as Nick showed up here at the IfA, he immediately hit the ground running and got involved in the TESS Giants Transiting Giants project, leading to the first planet discovered from that project. So it was led by Nick. He then proved his breadth of research ability by then immediately going and working on something completely unrelated to planets, nailing that as well, and then jumping back to the planets train to help us find more and more objects that I'm sure he'll tell you more about later. But I'm just here to talk about more of the fun stuff. So while Nick was doing his PhD, we got to go to a lot of conferences. And so one great example was the Aspen workshop, which we went to in 2023. So here we have some pictures of Nick and myself. As those of you know, Nick growing up in learning how to ski and doing tricks at the age of 6, he was by far the best of all of us. But we got everyone together, and we actually got a fair amount of the academic lineage. So here on the right in the yellow, that's actually Dan's PhD advisor. But we had to get a stand-in for Dan just in case anything happened. But yeah, since then, that Nick has been to a whole bunch of other conferences. So here are just a bunch of presentations that he's given all over the country and over the world. So I think we have Las Vegas, New Orleans, Boston, Las Vegas. I already said Las Vegas. Hawaii. Another one from Hawaii. So, all right, at least around the country, and I'm sure that'll continue Nick continues to do great things in his career. And so Nick continues to be successful. So here at UH, he was awarded the ARCS award. So I don't know exactly what that stands for, but it's an award given to the top graduate students at the university or in Hawaii. And then he was also awarded a Student Excellent in Research Award for the work that he's done as part of his PhD. So it's been really amazing to see his success, and even the public has caught up with it a little bit, where he's done interviews with Hawaii Public Radio somewhere here. I don't know exactly where that is, but Nick is going to continue his success as time goes on. So his next step will be headed to Yale University as the Yale College or the Yale Center for Astronomy and Astrophysics Prize Fellow. There's only one of these prize fellowships given out every year, and so this is a huge honor, and we're really proud of what Nick has done in getting himself there. And I'm happy to let you hear all about it from the man himself. So Nick, why don't you take it away?
Wow. Thank you so much, Dan and Sam. That was a real trip down memory lane. There are my slides. All right. Wow. Yeah, thank you so much. It was amazing to relive the path that took me here. It's been quite a 6 years of working on this dissertation. I'm really thrilled to be able to present the work that I did here over the last 6 years. So thank you all for being here in person. Thank you to everyone who's joining on Zoom to hear about the work I did during my dissertation. And I have covered a broad range of topics in stellar astrophysics and exoplanet science during my time here. And today I'm really excited to share the work that I've done that focuses on how stars evolve and the influence that stellar evolution has on the planets that orbit them. So I primarily spent my time looking for new planets and trying to characterize them precisely. So exoplanets are just any planet that orbits a star outside of our solar system, so any star other than the sun. Up until the end of the 20th century, the only planets that we knew in the universe were the ones in our own solar system. And so it's pretty recent that we've understood that planets are common. And what we've learned about them is that they have a really broad range of characteristics. So this is just a collage of some artists' images of what exoplanets might look like. And what I really just want to highlight is that they are ubiquitous and diverse. We expect that on average, every star in our galaxy hosts about one planet, and these planets have a really broad range of characteristics, from small rocky objects to giant gas giants like Jupiter. And they also orbit a wide variety of stars. So this is just a histogram that shows the cumulative number of exoplanet discoveries per year. And this shows how recent this field really is. Only in 1995 was the first planet confirmed around a sun-like star. And since then, it's exploded. And I just want to highlight that on October 11th of 1995, telescopes at the Lick Observatory in California were pointing at 51 Pegasi, measuring its mass and confirming that this planet existed. This was a very notable day for astronomy, because I was also celebrating my first birthday. My sister was celebrating her 6th birthday. This was a fun little tidbit that I found while I was writing my dissertation. And since then, there have been a few more birthdays and a few thousand more exoplanets. And we've seen a really wide range in the properties of these planets. So here I'm showing the measured mass of a planet on the y-axis against its orbital period on the x-axis. And you can see that the transit method and the radial velocity method are kind of two primary ways that we find exoplanets. And they're the main methods that I use during my research that I'll describe in more detail later. But they carve out kind of unique regions of parameter space here. But what we found is that these planets have a wide variety of orbital separations, from less than a day to millions of days orbital periods, and a really wide range of masses as well. And some of these were incredibly surprising, given the properties of planets in our own solar system, including that very first confirmed planet around a sun-like star 51 Pegasi b, which was in this class of planets that are very massive and on incredibly short orbital periods. And we call these hot Jupiters. So these hot Jupiters are great test beds for a lot of the kind of dynamics and atmospheric studies that we're interested in, and have been a big focus of my research. In addition to a variety of characteristics of the planets themselves, we've found planets orbiting a wide variety of stars. So this is what's called a Hertzsprung-Russell diagram, or an HR diagram. It has the stellar luminosity on the y-axis against the temperature decreasing on the x-axis. And most stars spend almost their entire life. So the main feature of this is the main sequence, which is kind of that diagonal trend across the HR diagram. And stars spend the majority of their lives on the main sequence. So a star like the sun, which you can see is right here, spends about 10 billion years on the main sequence before it evolves into a red giant. And we've found planets around stars in almost every corner of the HR diagram at this point. And in addition, we're starting to find planets around stars of a wide variety of ages. So as a star like the sun evolves, runs out of fuel in its core, it cools off, it grows larger, more luminous. And this really dramatically impacts the environment of a planet orbiting that star. So I want to consider the co-evolution of a star and its planetary system. So just to give a quick crash course in kind of the full lifetime of a planetary system, you start with a big cloud of gas and dust that collapses into a spinning disk. At the center of that spinning disk, you form a young protostar in the pre-main sequence. And then from that disk of material, planets form, and eventually the remaining gas and dust is blown out of the system, and you're left with this planet orbiting its star, or some system of multiple planets. Eventually, the star will end its main sequence lifetime, evolve into a red giant, swells up, becomes more luminous, and eventually blows off its envelope, its outer atmosphere, and you're left with just the inert core of that star as a white dwarf and some disk of material around it. So this is the case for a star like the sun. The sun is about halfway through its main sequence lifetime at this point. But the reality is that this is a very simplified picture. And this seems like kind of a clear timeline of the lifetime of a planetary system. The reality is that there are some big mysteries that remain in this process. In particular, at these transition points between the different phases of stellar evolution. So for example, the formation and migration of some classes of planet are still open questions. Whether planets can survive to the late stages of stellar evolution, and at what point planets are engulfed or ejected and destroyed. And what I've focused on during my dissertation, and what I'll share with you today, is that by studying planetary systems around evolved stars, we can learn a great deal about the processes that govern these transitions between different phases. And by building this larger population of planets orbiting evolved stars, we can piece together the full lifetimes of planetary systems. To motivate this, there are a few specific questions that I've focused on answering during this dissertation. They are, can planets survive stellar evolution? Why are some hot Jupiters so inflated? And how do the orbits of giant planets evolve? But before we can get into answering these questions, it's important to trace the evolution of the stars themselves. And so I'll start with step 0, which is modeling the evolution of stars and precisely characterizing them. So this is something that I spent quite a lot of time on during my thesis, working with Jen. And to motivate this, I'll show a simplified version of what's happening in the interiors of stars. So a solar mass star is shown in the top left. This is a star of roughly the mass of the sun. And what I'm going to focus on is just how energy is transported in different regions of the stellar interior. So in the core, energy is primarily transported through just radiation. But in the envelope of these stars, like the sun, you have convective motion that transports energy. When a solar mass star evolves into a subgiant and then a red giant, it maintains this same structure. You have a radiative core and convection in the envelope. But a star that's more massive than the sun on the main sequence actually has the inverse structure. It has convection transporting energy in the core, and the envelope is primarily radiative. But as a star like this cools and evolves into a red giant, its core, its convective core quenches and becomes radiative, and you develop this growing surface convective envelope where convective motion is actually transporting energy in the envelope. On the main sequence, this divide is around 6,200 Kelvin, which corresponds to about 1.2 solar masses. This is typically called the Kraft break for reasons I'll get into in a little bit. But what's very interesting is that stars that are more massive than the sun actually cross the Kraft break during their evolution and flip their internal structure. And the reason that I'm focusing on where convection is occurring is that it plays a role, a very key role in two things that I'll be talking about today. So the first is that convective envelopes can generate large magnetic fields. So the convective motion of ionized plasma can generate a large dipole field. And these convective envelopes can also very efficiently dissipate energy through tides. And this will come back later. But let's focus on the role that the magnetic field plays first. So this is a Keel diagram. So it's similar to an HR diagram, but we have the surface gravity of the star on the y-axis now. And what this is showing is the rotation rate for stars of a variety of characteristics. And this is modeled by Van Saunders and Pinsino in 2013. And what you can see is that because based on the red color for those massive stars, they're all rotating extremely rapidly. You have this very fast rotation. They're spinning with very short rotation periods. But stars that are cooler than the Kraft break at about 1.2 solar masses, so that line is right about here, show slower rotation and a wider range of rotation rates. And what we found is that because these cooler stars with convective envelopes can drive these large magnetic fields, they actually gradually lose angular momentum through interactions between those magnetic fields and their solar wind, and they spin down over time. So they break in their rotation. And we can leverage this relationship because we know that stars spin down over time. By measuring the rotation period of a star, we can get an estimate of its age. We can see how long it's been spinning down. So what I'm showing here in this figure is the rotation period against the effective temperature for a series of stellar clusters. And each of the stars of the same color share roughly the same age. They formed in the same cluster at around the same time. What you can see is that as we step up in age, as the clusters get older and older, the rotation periods get longer and longer. And so that gives us a way to benchmark the rotation period as a function of age. And so now, given some measurement of the temperature of a star and its rotation period, we can infer an age for it remarkably well. And this relationship has been really well characterized up until about the age of the sun through studying clusters and their rotation rate. But when we had the ability to independently measure rotation periods and ages for a wider variety of field stars that were older than the clusters that we'd used before to calibrate this relationship, we found that some of these stars deviated from the predicted spin down trend. So now what I'm showing here is, again, the rotation rate is on the y-axis, but now I have age on the x-axis, and it's divided up into different mass spins. And so what you can see is that if you assume this kind of standard spin down law that we calibrated against the clusters in blue, it predicts longer rotation periods than what we measure for a lot of these stars from Kepler. And the idea here that was presented by Van Saunders et al. In 2016 was that stars enter a phase of weakened braking. They're no longer spinning down at the same rate. They maintain this rapid rotation later into their lifetime. And so this is likely due to some change in the magnetic field structure that prevents the stars from losing angular momentum at the same rate. So during my thesis, I trained an artificial neural network on a large grid of stellar evolution models that could very rapidly emulate what a stellar evolution code does. And because of that, I could actually sample the parameters of these models for how stars spin down and create a big hierarchical model that used this sampling approach to constrain these braking parameters with a large sample of stars. And the two key parameters that I focused on were kind of the overall strength of braking before weakened braking sets in, which is represented by this FK parameter. What's called a critical Rossby number, which is just kind of a proxy for when this phase of weakened braking starts. And it's very important to know precisely when weakened braking sets in, because if we want to use gyrochronology to accurately measure stellar ages, it's important to understand whether we're in a regime where gyrochronology is an effective estimator for age. And so with this artificial neural network, I was able to place new constraints on the onset of weekend braking and realistically calibrate when gyrochronology is a useful age estimator and what its uncertainty should be. Aside from gyrochronology, another approach that we use to calibrate, precisely characterize stars is astroseismology. So we have a very quick crash course in astroseismology, which is just that it's the study of pulsations in stellar interiors. Just like sound waves propagate through our atmosphere from my vocal cords to your eardrums, sound waves propagate through the insides of stars in the plasma. And cool stars, the ones with convective envelopes that I've described, typically exhibit what are called solar-like oscillations, which just means that the kind of structure of their oscillations is similar to what we see in the sun. And we see these as brightness fluctuations over time by staring at these stars. And by measuring the frequencies, we can find, so this is just kind of a Fourier transform of the brightness of a star over time. And you can see that there's kind of two key features. There's this envelope, this roughly Gaussian envelope of pulsation modes, and then there's this characteristic separation between pulsation modes of the same order. And so these two observable parameters are actually incredibly powerful for characterizing stars. Just by measuring these two properties of the oscillations, we can get a great constraint on the radius and the mass of a star. And we've been able to do this for evolved stars, including those that host planets. So this is an example from a paper that I published earlier this year, showing that we detect these solar-like oscillations in a red giant that hosts a planet. You can see that characteristic Gaussian envelope, and I've identified specific modes. And so with this, we're able to very precisely measure the properties of the star and get a better understanding of the planet that orbits it. So with these methods for characterizing stars precisely, we can start to answer some of the questions about the planets that orbit them. So the first question is, can planets survive stellar evolution? And the best way to answer this question is to look for them, right? We want to see if we can build a large sample of planets orbiting evolved stars and understand the kind of occurrence of planets at late stages of stellar evolution. So a large part of my dissertation work has been building a pipeline to find new planets orbiting evolved stars. And I predominantly use the transit method. So very quickly, the transit method is just an approach where you look for periodic dips in the brightness of a star over time. If you're looking at a planetary system edge on, every time a planet completes an orbit, we'll block some fraction of the star's light. You get a dip. And I use data from NASA's TESS mission, the Transiting Exoplanet Survey Satellite, to search for these transits. And TESS observes broad regions of the sky. It's a survey satellite. This is just an image of what one of the full frame images looks like. So this is a huge region of the sky that contains millions of stars. And so because there are so many stars, it's necessary to produce kind of automated ways to search for these planets. And one of the benefits to having so many stars to be able to search for planets around is that planets around evolved stars are actually pretty tricky to find. And I'll explain why. So this is an example of what a single transit for a hot Jupiter orbiting a main sequence star looks like. It's very deep, very clear signal to noise. You can pick it out by eye. But if instead this hot Jupiter were orbiting a subgiant star, its transit would look like this, right? So it's much shallower. The signal to noise is lower because the stars become so much more luminous. And it's also longer duration because the physical size of the star is swelled up. And so because they're so difficult to find, it's necessary to search a very large sample of potential hosts. It's also very easy to accidentally remove these transits when you're producing your light curves. And so we produced our own dedicated pipeline. So this is an open source Python package that produces light curves, which is just the flux over time for these hosts. And I won't get into the details, but it's a pixels to planets pipeline where we take cutouts from those full frame images and remove the noise and search for these transits. So you can see the little dips are preserved. And it was necessary for us to produce our own dedicated search for planets around evolved stars because other large-scale search efforts, which predominantly search for planets around main sequence stars often remove these transits accidentally. So this is an example of one of the planets from our survey that was removed by another pipeline, but you can see that it's nicely preserved in our light curve. So we produced millions of plots that look like this and have a lot of fun flipping through them to confirm all these planets, or to detect all these planets. And then once we found a candidate that looks promising, we can follow it up with the other method that I mentioned earlier, radial velocity. So radial velocity is another approach for finding planets. And what you can see here is that as the planet orbits the star and the planet are actually both orbiting the center of mass of the system. And so the star is wobbling in the sky, and we can't measure its motion in the sky, but what we can do is measure its motion towards and away from us. And we can do this by taking high resolution spectra of the star and measuring the shifts of specific features in that spectrum due to the red shift and blue shift as the star moves towards and away from us. And we do this with instruments like high-res and KPF on the Keck-1 telescope. So I spent a lot of nights over the past 6 years staying up and staring at the sky. I don't use it when the laser is on, but it's way cooler. And with these two types of observations, with transits, radial velocities, we can actually learn a remarkable amount about these planets. We can learn their orbital period, the radius of the planet, the mass of the planet, and therefore its density, the temperature, its orbital eccentricity, which is a measurement of how circular its orbit is. And so just from these two types of observations, we can really characterize these planets precisely. And what have we found? So this is what the Keel diagram of planet hosts, transiting planet hosts looked like in 2018. So this is right before TESS launched. And you can see that it's really dominated by stars on the main sequence. And there were debates about whether these planets should exist at all, whether they should be destroyed by tides over main sequence lifetimes. And I've highlighted a few kind of high impact results from Kepler and K2 that show there's a small but growing sample of planets that have been found around subgiants and red giants. And studies from these K2 planets indicated that planets around evolved stars should be about as common as their main sequence counterparts, but it was limited by a very small sample size. And so this is what the Keel diagram looks like now. So this is including all of the discoveries from TESS. And what I want to point out is that there have been quite a few confirmed planets from TESS, but they again mostly lie on the main sequence. And so all of the TESS discoveries are shown by black points. Everything from our Giants Transiting Giants survey is a red star. The confirmed planets are the filled red stars, and candidates are the open red stars. And you can see that we're really pushing into an empty parameter space in terms of stellar hosts. We're getting up to similar sizes as the hosts from Kepler and K2 and filling in this region that's been mostly empty. So with this growing sample of planets that have been found around evolved stars, we're able to answer some other very interesting questions about the properties of these planets. So one of those is, why are some hot Jupiters inflated? And this has been a very interesting question that's been longstanding in exoplanet science. And it was discovered when we had a large population of these hot Jupiters, massive planets on short orbital periods, that there was a population of them that were much larger than we would have expected based on atmospheric models for them. And you can see that the planet radius on the y-axis against the incident flux, the x-axis has this very steep ramp up beyond some threshold. This is about 150 times the flux received by the Earth. And beyond that, you get this really steep relationship where the more incident flux the planet receives, the larger it is. And so we've been trying to understand the mechanism behind this inflation. And the very first planet from our Giants Transiting Giants survey actually fit into this in a very interesting way, in that it was not inflated. So this is TOI 2184, which I published in 2022. You can see it sits down here right at the bottom of this trend. And so it's more consistent with planets that receive lower incident flux. Though it's not totally unlike things that are around it, it provided interesting insights that there may be some other mechanisms at play here. The most recent planet from our survey also fits into this in a very interesting way. So this is a planet that I published a discovery paper for earlier this year. And you can see that, again, it's not inflated. It's kind of down in this region. And what I'm showing with this line that traces back is where we expect it was on the main sequence. This is about the incident flux we received on the main sequence, and since then, stars become more luminous now out here. And so what this shows is that despite this planet receiving a lot more incident flux than it did on the main sequence, it doesn't appear to be dramatically inflated. We can also compare it to a couple of those systems from K2. So K297 and K2-132 are shown there. And these systems are remarkably similar to this TOI in that their host star is about the same, roughly the same temperature and radius. The planet mass is about the same. The orbital period is nearly identical. And so everything about them is very similar, except for the fact that the K2 systems are significantly inflated, while this TOI is not. And so because of these, this single difference, we went looking to see if there were other clear differences that could help explain this. And one that came up is the orbital eccentricity of these planets. And so the eccentricity is a measure of how circular a planet's orbit is. Something with zero eccentricity is on a perfectly circular orbit, and the higher the eccentricity is, the more elliptical the orbit is. You can see that in the radial velocity, for a circular orbit, you get this nice sine curve. For an eccentric orbit, you get a deviation from that. And these are both consistent. The K2 systems are both consistent with non-zero eccentricities, and those are inflated. Well, the test system is most consistent with a circular orbit, and it is not inflated. So now we can consider why this might play a role in the inflation that we see. And I'll just very quickly introduce the idea of tidal heating. So a planet on an elliptical orbit with a non-zero eccentricity, as it orbits its star, it will make these approaches that are closer to the star, where it's entering a region of stronger gravitational force than when it's at its most distant approach. And because of this, it's getting stretched and pulled as it makes its orbit, and that causes the planet body to distort and introduces heat inside of the planet through that friction of the body kind of squeezing and contracting as it makes its orbit. And so if we look at these systems where you have eccentric and inflated planets and compare them to the circular, not inflated planet, provide some evidence that maybe tidal heating is a significant contributor to the inflation of these planets, depositing heat deeper in the planet's atmosphere and allowing it to puff up. To really understand this, we want to build a larger sample of planets around evolved stars and get precise constraints on their eccentricities to see if this trend continues. So circularization is not the only change that these planets' orbits undergo, and I'll discuss some of the other dynamical evolutions that we've studied. So the third question that I want to answer is, how do the orbits of planets evolve? So this is a really interesting question to ask, because not only does it tell us what the late stages of planetary systems look like, what the dynamics are after the main sequence, but we can actually use what we learn about how orbits change at late times to make inferences about the formation pathways for these giant planets. And to explain why that is, I'll introduce the idea of hot Jupiter formation. So hot Jupiter formation has been a long-standing question in exoplanet science as well. It's unclear how you end up with these very massive planets on very short orbital periods. And when they were the first planets that we discovered, it became kind of an urgent question to start answering. And people came up with a variety of theories for how you can form these giant planets on short orbital periods. And two of the ones that have been dominant are this idea of disk-driven migration, where you form a giant planet at a wide separation, and then before the disk of material dissipates, it gradually loses angular momentum through interactions with that disk and circles in, and you end up with this giant planet on a circular short orbital period. And then there's the idea of high eccentricity migration, where again you form this giant planet at a wide separation, and then through some dynamical interaction with either another massive planet in the system or a stellar companion, the planet is scattered into some highly eccentric orbit, often misaligned, and gradually through that tidal circularization process that I described, it will lose angular momentum and spiral in to the state that we see it. And so we can use the predictions from this to test these different theories. So one of the predictions is that disk-driven migration should provide circular, well-aligned hot Jupiters. So when I say well-aligned, I mean that the orbital plane of the planet is aligned with the spin axis of the host star. So this is a little diagram that shows what these different vectors are. Here's the stellar spin axis. The star is rotating like this. You have the orbital momentum axis of the planet, and the aligned systems have a zero obliquity, and the further you are from aligned, the larger that angle is. And so these high eccentricity migration cases should predict misaligned orbits because of the dynamical scattering that produces these misaligned orbits. And at late times, you would still expect to see these misalignments. And so what do we actually see in the data? Well, we can measure this. We can measure the obliquity through something called the Roster-McLaughlin effect. And so this is kind of a combination of the transit method and the radial velocity method that I described. You take radial velocities during a planet's transit. And in addition to that kind of overall trend that you get from the motion of the star, you get this additional component that's caused by the planet blocking regions of the stellar surface that are either blue shifted towards you or red shifted away from you due to the star's rotation. And a planet that's well aligned will have this symmetric kind of sinusoidal looking signal. And the more misaligned the planet's orbit is, the more you deviate from that symmetry. And so if we look at the stellar obliquities that have been measured for these hot Jupiters, and now I have the stellar obliquity on the y-axis where 0 is well aligned and anything above that is more misaligned, against the effective temperature on the x-axis. And you can see that for the cool stars, the systems are generally well aligned. There's this big pileup near 0 for the obliquity. And for the hot stars, you have this really broad range of stellar obliquities that we measure. And so this is, the divide corresponds to about 6,200 Kelvin, right around the Kraft break. And so this is the division where the stars have those deep surface convective envelopes. So I said, remember the tides is the third act, the tides are coming back. You can see that there's a clear difference in these distributions. And one of the predictions is that tides can damp out this obliquity and realign the systems that are cool and amenable to those tidal effects. And so one of the questions that we want to ask that can help us understand the timescale for these processes and its dependence on the existence of a convective envelope is, what if you have a star that starts on the hot end of this distribution and cools off and develops that deep surface convective envelope and crosses the Kraft break? And very few, if any, measurements had been done for this class of star. And so we wanted to undergo a targeted search for systems that had crossed the Kraft break and measure their obliquities with the Roster-McLaughlin effect. And so we're able to do this over the past few years for 5 targets, and I'll highlight 3 of them that showed up in a paper that I wrote last year. And so these are 2I1181b. And we measured the Roster-McLaughlin effect with Keck high res. You can see that it has that nice symmetric signal. It appears to be well aligned. It's consistent with an obliquity of 0. The next one, 6029, also has a very low obliquity. And the third one, which we observed with Keck KPF, also shows that it's consistent with a well-aligned orbit. So this is interesting. This is surprising because these systems are sitting just on the cool end of the Kraft break. They've only had these surface convective envelopes for a very short fraction of their lifetimes, maybe hundreds of millions of years. And so how have they had time to efficiently damp out that obliquity and end up in this cool, well-aligned population? So what we wanted to do is investigate if we could model the damping of this obliquity and model how a planetary system could go from misaligned around a hot star in the main sequence to well-aligned around a cool evolved star. And so we expanded on existing models for the damping of orbital period and stellar obliquity. And I won't get into the details, but I do want to highlight that the timescale for this damping depends very strongly on a few features, such as the orbital separation and its ratio to the radius of the host star, the density of the host star, and this property Q star, which is just a measure of how efficiently energy is dissipated in the envelope of the star. all of these things will change dramatically as the host star evolves. And they will all decrease. And so the time scale will get much shorter as the host star evolves, causing you to much more efficiently damp out both the period and the obliquity. And the problem this introduces is that planets enter this phase of runaway in spiral. So you can see on the top, I have the orbital period as a function of age. And you can see that it very gradually moves in until it reaches this critical point where it just plummets into the star and is engulfed. And so this happens very quickly before the planet has a chance, before the system has a chance to realign. You can see that it stays at basically the exact same misalignment angle and then snaps into alignment as it gets swallowed. And so one possible solution for this is that the damping of this spin-orbit alignment may be more efficient than the rate of orbital decay. And so if we allow this enhancement to the efficiency of the realignment timescale, we can produce a model where the system realigns before the planet is engulfed. So the planet survives and the system aligns. And this is great, but it isn't us just putting our thumb on the scale and saying this works. There are some theoretical reasons why you might expect there to be a difference in these efficiencies. I'll list a few of them here. I won't get into the details, but I'm happy to chat about them in more detail. But there are some ways that you can explain how the efficiency of this obliquity damping is enhanced relative to the in-spiral rate, and it produces very similar predictions to what we see. And so this allows us to place a track on this plot that I've shown a few times, which is going from some broadly misaligned main sequence hot host star to this well-aligned subgiant in a pretty short time scale. So this supports the idea that with the inclusion of this efficient realignment, high eccentricity migration can actually explain all of the distributions, the full distribution of obliquities that we see, right? You can have all of these planets that are scattered into a wide range of obliquity angles, and then in the presence of convective envelope, you can quickly realign those and get that difference in distributions across the craft break. So by studying evolved stars, we actually got unique evidence for the formation pathways of these planets. So I want to wrap up by just quickly summarizing some of the work that I did. Dan and Sam listed these papers earlier, but I just wanted to share them again and show that I've mostly worked on planets and stars, but I've covered kind of a wide range of things. But I've also been very lucky to work with a lot of incredible collaborators and do quite a lot of observing, and so I've contributed to 22 other papers as a co-author. And what all of these have done together is started to fill in some of the gaps in our understanding of this timeline of the evolution of a planetary system. And hopefully by studying planets around evolved stars, we can start to answer questions about both the formation and the fates of planetary systems and fill in kind of the full lifetime of a planet. So I have a lot of people to thank. I'm incredibly lucky to have worked with so many amazing people, but that means that I have way too many people to acknowledge. So many people are responsible for helping me get here. I really want to thank Dan and Jen and Sam for being excellent advisors and making this all possible. Everyone on my committee, thank you for the feedback you've given, the support you've given. At the University of Washington, I had some excellent mentors who really supported me and got me where I am today. At NASA, as Dan mentioned, I worked in an incredible office. I think we actually worked in the same office, like the exact same room, which is crazy. Just a few years apart. But yeah, I had some fantastic colleagues and mentors there that really made this all possible. I've worked with so many great people in the field that I couldn't possibly list all of them, but I listed a few. Everyone here at the IfA who enabled this, staff and the admin, everyone in my cohort. It was a rocky start, but we made it through. Everyone at the IfA, I mean, so many friends. I couldn't possibly list all of them, all of the grads and postdocs. It's been just a blast, even though it's been very challenging. It's been so much fun. I have a lot of friends who are genetic counselors for some reason. I think some of them are on Zoom. Thanks for joining. And my family, thank you for flying all the way out here. It's incredible you made it out. And Marty and Raya, who sadly couldn't be here. They're watching on Zoom. And Brittany, thank you for making this happen. You should get the PhD. So with that, I'll leave up a summary of my main conclusions, and I'm happy to take any questions. Thank you.
Thank you, Nick. We have time for questions. Let's start in the room. Any questions for Nick? Alexa.
Thanks for the really nice talk there. So you kind of motivated some of the parts of your thesis, particularly the different methods of migration, by saying that we could try to use the obliquity as a way to differentiate between those two. Then basically you went and found that the high eccentricity migrations coupled with the damping can explain all of these different obliquities. So is there a way now that we can backtrack to still distinguish between the disk migration versus the high disk migration?
That's a great question. So basically, are you asking whether we can determine whether these things were misaligned here or whether they came from this aligned population? It's challenging to do so, but I think we can basically make a statistical error. If we build up a large enough sample of things that sit on this side of the craft break and are well aligned, and even with just the 5 that we have, it's incredibly unlikely that we would have drawn 3 things that were previously aligned on the main sequence. The one thing that we can do to better understand the difference between these is get a sense of the time scale for how long it takes this realignment to happen. And to do that, I think the best way is to kind of get precise ages as best we can, and kind of trace a finer grid of temperatures and say, at different evolutionary phases, what is the misalignment, and can we kind of trace this all the way back to a misaligned system that gradually makes its way down? That's a good question.
Okay, more questions. If anyone online has a question, please use the raise hand feature and I'll call on you. But in the meantime, let's go to Anne.
In your slide 39, you show a diagram that's shown a lot, but it has yes, that thing in the middle. It has a big flaw in it.
This one here?
No, below that.
This, yeah.
Yes. So you understand what that? People show this picture all the time.
Yeah, this is kind of a cartoon version of what radial velocity is. The line shifts are.
Yeah, but what else is wrong? What's wrong with that diagram? People show it so much and it always bothers me.
No, I'm not sure exactly.
Enlighten us, Ed.
Well, the colors.
Oh, sure. Typically a much smaller range of wavelengths than whole.
No.
Or are you talking about the order of the colors?
The fact is that the colors move too. It's not just the line.
Sure, I think it's relative to some background.
Yeah, but the background moves. The
Yes.
colors. Okay.
All right, let's move on. Dan.
Sure. One comment. So on your tidal realignment plot with your model, so if you shift it over a bit, it seems like it would pass through the craft break multiple times. So can you comment on what would happen in your realignment if it develops convective envelope, then goes back and then crosses the craft break again?
Yeah, so something that I've since come to realize about this is that this is the track that's shown here is actually realigning at a later time than we expect these ones did. So this is a star that has actually gone across the gap and hooked back. So it's a star that's massive enough to hook on the Hertzsprung gas. And so that's what you're seeing here where it gets hotter again. And these have all realigned before hooking back. So these have all realigned kind of in this time scale, and they're a bit cooler, and so it happens closer to the craft break. But yes, what would happen if you kind of went back and forth across the craft break is from our very simple model, what would actually happen in practice is the efficiency would get higher for a little while it was on the cool side, and it would drop a little bit and then go back, basically stay where it is. In reality, it's a little bit more challenging to say, and something that I hope to model in more detail during my postdoc, which is kind of how much of a convective envelope do you need for this damping to be efficient? And basically, is it very strongly dependent on temperature, or is it more related to the structure? Yeah.
Okay, we have a few more minutes. Darren.
Yeah, hey Nick, great talk. This is a question about the tidal reinflation. I don't think of a good way to phrase this, but basically, so if you had a planet that was eccentric for say a while, but became circularized, and you observed it, right? Do you have a sense of how much time, how much time it would take for that planet to like deflate again after it's no longer eccentric? And like, how does that compare to like typical circularization timescales?
Yeah, this is a really excellent question.
Yeah.
And I think I'm not sure that the answer is very well understood. It depends on how efficiently the planet loses heat, which will depend on things like the structure of the atmosphere, its molecular composition, cloud structure, things like that. I think there have been models like the stuff that Daniel Thorngren does that show that after the heating mechanism switches off, the planet reaches an equilibrium state pretty quickly. So I think you'd expect that on the timescales that we see circularization occurring, that only in cases where we actually see an eccentric orbit would you expect the inflation from that tidal heating.
Okay, I think I saw Ben's hand up. Ben, do you have a question?
Yes, very nice talk, Nick. If you go to slide 69.
Oddly specific.
Well, it's just the normal plot. You showed it a bunch of times. Yeah, you tell a very nice story for why the stars that cross the craft break end up aligning very quickly. But then that obviously begs the question, why are there cool stars that are misaligned?
Yeah, so you're referring to these ones up here. There are a couple of reasons you might expect this. So one is that there are potentially stable orbital configurations that are not fully aligned. So even in the presence of convective envelope, Simon Albrecht has a great paper called A Preponderance of Perpendicular Planets, which is one of my favorite paper titles. I'll repeat it every time, which showed that you can kind of damp the obliquity until you hit 90 and then stay there. But again, these aren't specifically at exactly 90 degrees. And so another explanation could be that they are tidally detached. So the cuts that I made may have included some things that were a bit further out and aren't kind of in the regime where the tides are efficient enough, or these may be late arrivals and things that have misaligned more recently in their history. So definitely worth looking at more. But there are versions of this plot that go around where you don't see those. People who make stricter cuts about semi-major axis and stuff like that. Yeah.
Okay, let's have one last question since we're right in the hour. Anne, another one.
This is a question I would ask if I were on the committee. Would you describe the craft break and how he discovered it?
What was the question?
Would you describe the craft break and how he discovered it?
Yeah, so my understanding is that the craft break was an observed feature in the rotation rates of stars. I don't think I know the history well enough to talk you through the discovery of it. But essentially the rotation velocity from line broadening is much higher above the craft break than it is for stars that occur in the craft break. And so my expectation is that by measuring a variety of line widths for stars that are near this temperature, you could find a clear distinction. Yeah, I have to revisit it.
Okay, I think we're at the hour and we've questioned Nick enough, at least for now, the non-committee members at least. So let's give Nick another round of applause.